Hey folks, it's Murphy here, doing an AP Stats video on section 6.2b, which deals with not the transforming part, but the combining part of transforming and combining random variables. If anyone's listening from the future, the year is 2020, it's the day before a snowstorm. We've just been told that we're going to be doing things asynchronously, so I'm kind of putting this together at the last minute. I was originally planning on doing this live. So if it lacks the usual polish, then I apologize. But I don't want that to detract from the fact that this is a super, super important lesson. I kind of hyped it up last time with 6.2a towards the end by alluding to one of the finer concepts and one of the more important concepts, and also saying that the big conjecture that we deal with in this lesson is the second most important one in all of AP Stats. So despite the fact that this is a video, this is not something that you want to take lightly. You want to be able to leave this understanding what the main ideas are and how to work through problems. And if not, that's not the worst thing in the world because it's a video. You can always go watch it again. But just to recap a little bit with some of the objectives. Last class, in 6.2a, we learned to describe the effects of transforming a random variable by adding, subtracting, multiplying, and dividing by some constant. That was the whole linear transformation thing, which I'll review once again in a moment. But how we're going to go one step further this time is instead of dealing with constants, what we're going to be doing instead is taking one random variable, taking a second random variable, maybe even sometimes a third or fourth or 12th or whatever, and then combining those via addition or subtraction, and seeing how that does a couple things, like affect the mean and standard deviation of the final random variable outcome, and if everything happens to be normally distributed, if these are normal random variables, well then we could do some probability problems too. You know me, so you probably knew that the lead up to something like this might involve something kind of nerdy, and here we are. Me and my friends. Suppose it's just another weekend and we're playing Dungeons & Dragons. And I've got my Dungeons & Dragons character, Sir Murphington, a paladin, and he attacks a goblin. So the way that attack rolls in this game are determined is you take a die and you roll it. Suppose my damage is going to be calculated by taking 3 4-sided die, each having a face 1 through 4, and then rolling it. So I could either roll 3 different ones or roll the same one 3 times and add their face values. So I guess 4-sided die are in short supply, or at least they're not as ubiquitous as a number cube, a 6-sided die. So let's suppose my friend Frank says, instead of rolling 1 3 times, or rolling 3 different ones, why don't you just roll 1 die, look at its face value, and then multiply by 3. And for a moment, this actually happened, by the way. For a moment, we all contemplated whether or not that would be the same thing, if that would just be a quicker way to do it. But then we quickly came to the conclusion that no, it wouldn't. And one way to kind of compare these two things, the original like roll 3, add them up versus roll 1 and multiply by 3, is we kind of looked at the outcomes associated with each of these things. So let's look at Frank's idea. I take a die, I roll it 1 time, and then I multiply the outcome by 3. I'll call this the random variable 3x, where I'm saying that x is to be the face value of a random 4-sided die roll. So for starters, x is a random variable. Like by definition, it has a set of outcomes, 1, 2, 3, 4, and then a set of corresponding probabilities, which would just be 1/4 for each of those, because all the faces are equally likely. So what's the set of possible outcomes for 3x, which is to say, I take a random outcome of x and then multiply it by 3. Well, instead of 1, 2, 3, 4, I have their triples, 3, 6, 9, 12. And just as with the original die roll, with the original random variable x, all the outcomes are equally likely. Well, what about the actual situation that the game calls for? I take a die and I roll it 3 times and add those, or I grab 3 different versions of this thing and roll those and then add them. What would the set of possible outcomes be? Would it be the same thing as this, 3, 6, 9, 12? Well, with even a little bit of thought, we can conclude that no, it's not the same thing, because for instance, I could roll a 5 and a 1 and 2, and that'll give me a sum of 8. 8 damage, not bad. But also, 8 isn't even one of the possible outcomes for the 3x idea. So what are the possible outcomes here? Well, really, it's anything from 3 through 12. And another important thing to acknowledge is that not all of our outcomes for x plus x plus x are equally likely. There's only one way to get a 3. You roll a 1 and a 1 and a 1. But if I want to find another way to roll an 8, for example, I could roll 6 plus 1 plus 1. I could roll 4 plus 2 plus 2. So just based on that alone, just based on the raw sample space, we know that 8 is more likely than 3, and we can imagine how some of these outcomes would be more likely than others. So then the final question then, I think which is now obvious, are the distributions of these two damage calculating methods equivalent? In other words, is Frank's 3x equal to the game's x plus x plus x? And if you look at this strictly through an algebra lens, then it looks like, well, yeah, that's what this means. X plus x plus x is 3x. But get yourself out of the mindset of thinking about x as some like algebra variable. It doesn't work that way. If we think of x as a statistical random variable, then maybe the normal arithmetic rules don't apply. And we've probably seen stuff like this before. Like think about when you multiplied, I'm pretty sure most of you did this, when you multiplied matrices, either in algebra 2 or geometry or whatever. Like think about the product of matrix A times matrix B. Not only is it not always AB, but sometimes it doesn't even exist, depending on the dimensions of those matrices. So when we have a variable that's not necessarily representative of a real number, but some abstract quantity like a random variable, then maybe these rules don't even apply. And it turns out in this case that no, they don't. 3x in stats world is not equal to x plus x, when again, these x's are representative of random variables. They have different outcomes, and then when the outcomes are the same, like 3 and 3, they have different probabilities associated with them. So most of this lesson is going to be comparing the 3x part, which was kind of like what we did in 6.2a, taking a random variable and multiplying by a constant, versus this new thing, combining random variables, which has a lot more variation, I think we should acknowledge, or a lot more complex of a variation because it has 3 different die rolls instead of essentially 1. So let's see how that pans out by first comparing it to some old stuff. I'm not going to linger too long on this page because I just straight up ripped this off the note key from 6.2a, but this is what we did last time in 6.2a. We dealt with linear transformations. We looked at how that affected the spread, the shape. Spoiler, it didn't really. How it affected the mean, which it did in a very predictable way. We would add the constant, we'd multiply by the scalar constant. And then in terms of the spread, adding didn't do anything for us, but multiplying sure did. Also, one more small note, I suppose, that I have with an asterisk on the bottom is that e of x and mu sub x are the same thing. They both represent a measure of center for a random variable. They both represent the mean, and we should be comfortable using these two terms interchangeably. I led up to this, I should say, by looking at this example of grapefruits, and then grapefruits and oranges, and then us combining them via adding a random element of each random variable or subtracting them. And what we saw, I think contrary to what some of us initially guessed, is that whether we're adding or subtracting these, the range is added, which was interesting. I could basically kind of combine these two things into one and say the range of x plus or minus y would be the range of x plus the range of y. And we know that range is a center of spread. Not a very good one, not a very popular one, but it's a measure of the variation of each of these variables. So I demonstrated it with range because it's nice and easy to calculate, but spoiler, this is going to be true with variance as well. The variances are just going to add, whether we're adding or subtracting the two random variables involved. So here it comes. This whole page is kind of dedicated to seeing what happens if I take two independent random variables x and y. And I'll harp on that independent part later. And kind of differentiating between the 2x, that was 6.2a, versus the x plus x, which is this new stuff. So suppose I take x and y, and then also by the end of this, I'm kind of hoping we'll be able to see that this could extend to more than one, or I should say more than two random variables. Like if I do x plus y plus z, or if I have the same random variable that I just sample from over and over again, like x plus x plus x, like on the previous page. But let's call this the sum of random variables t. X plus y is going to be t for total. Let's talk about how we would expect that to affect the mean of t. How would t's mean relate to x's and y's means? Well, it'd be their sum. I don't think that one's too hard to imagine. The variance, though, that's kind of the big deal here. The variances are going to add. The variance of t is going to be equal to the variance of x plus the variance of y. And I think if we think about how variance relates to standard deviation, then we can kind of look at this whole ordeal in a new light. Remember that variance is really just the standard deviation squared. So what I have is sigma sub t squared equals sigma sub x squared plus sigma sub y squared. And I guess I could solve for this new standard deviation by taking the square root of both sides. Like, that's fine. But I feel like this is more interesting because you should look at this formula right here and think that it looks really familiar. Something squared plus something else squared equals new things squared. That should sound to you like the Pythagorean theorem. because it's actually what it is. And I can kind of demonstrate it too. Again, this only works with independent random variables. And again, I could kind of harp on that later, but I think the best way to show this is with the notion of vector space, which if you're a physics person, you might know what that is. I don't know how much you get into stuff like this with calculus or even computer science. There's definitely a course in college called linear algebra that deals with this. And vectors usually go hand in hand with matrices. But suppose I have a vector that's representative of the standard deviation of x. So let's say this is my vector x. Important to note here is that it's independent of y. If I had a vector that was not, that wasn't representative of x and y being independent, it might look something like this. It has a horizontal as well as a vertical component. It has an x and y coordinate. So that would indicate that x and y are not independent. Independence in vector space kind of means that each vector is going to stick to its own axis, so to speak. So let's say I have this representative of sigma x. I may have lost you with the notion of vector space already, but trust me, if you follow this, it's going to make sense. If I have sigma y, again, if y is independent of x, then it's going to exist exclusively on the y-axis, which means it doesn't have an x component. The x coordinates of each of these things are 0. It's only y's. And if we remember how to add these, suppose I want to add these random variables x and y and see what that would do to sigma. Maybe you remember how to add vectors. Again, I don't know if that's a thing that you learned. But essentially, we would attach them head to tail. So if I just shift this sigma y over and attach head to tail, then what I would do to look at the sum of the vectors is basically just go from the beginning of one to the end of the other. And suddenly, I have a right triangle where one leg is sigma x, the other leg is sigma y. So I end up here with sigma of x plus y. You can imagine if it was x minus y, I would just be dealing with like the negative. I'd be in different quadrants where one of these things is negative. But it works the same way. I'd still end up with a right triangle where the blue squared plus the magenta squared equals the green squared. And actually, this part's kind of interesting too. I think. But suppose it wasn't. Suppose we didn't have a right triangle. Suppose they weren't independent. If I had like, I'll do it in a different color, I guess. Well, I did blue already. It's probably not something I want to be wasting video time on. But anyway, if I had like this or something, and I wanted to look at my sum vector here, well, clearly one of these vectors is not independent of the other. There's some association between them. And if I wanted to try to calculate this, in stats terms, it would be something like the variance of x plus the variance of y plus 2 covariance of xy. It's a function with 2 inputs. This is more than you'll need to see. I'm just having flashbacks to like my senior year of college when I had a stats class involving this sort of thing. And I think it's really neat to acknowledge because maybe you don't recognize this, but what this is very similar to is the way you would relate sides and angles in a non-right triangle to each other. And that's with the law of cosines. If this were the law of cosines, it'd be c squared equals a squared plus b squared minus 2ab cosine whatever, right? So literally, this whole process is just doing the Pythagorean theorem over and over again. And just like the Pythagorean theorem has a conditional that it only works with right triangles, this whole formula right here that I've got starred only works if x and y are independent. It also works with differences, like I said. The mean would be just the difference of the means. The variance would still be the sum. Thus, the standard deviation sum would be the same thing. And then we have this. For the standard deviation of x plus or minus y, it's going to be equal to the Pythagorean theorem, essentially. We should think of this. This is what's going to be in the no key. But again, there's limitations on this. I've seen the AP test be very tricky and present to you problems where x and y are clearly not independent contextually, and thus you can't actually even calculate the standard deviation. And it all comes down to when x and y are independent. Either we need to be told that that's the case, or we need to be able to intuit it somehow. So that's only the case with the variance and the standard deviation. However, I have here in my second little note thing that the means can still be added and subtracted, like E of t and E of d are going to still be this, whether or not x and y are independent, but the whole standard deviation thing, the whole Pythagorean theorem of stats, that only applies when x and y are independent. As far as shape goes, we already hit center spread shape. It depends. It really depends. There's going to be some cases where if you combine random variables, they end up looking goofy. They end up having something to do with what the original distributions looked like, obviously. But if let's say x and y are both normal distributions. If I combine them, if I look at the shape of x plus y, or even x minus y, something about normal distributions, man. They just pop up all over the place. So if I take something normal and combine it with something else normal, the result is going to be normal. So take this page. Make sure it makes sense to you. Go back maybe like 5 minutes into this video and listen to this all again if you have to. But this whole thing about the Pythagorean theorem of stats and only applying conditionally or having limitations, that's important to acknowledge. The rest of this video is us kind of gonna getting good. We're kind of gonna just be getting good for the rest of this. At least sit through a couple of these problems before we move on. Try them on your own if you'd like to, but I'm gonna power through this. Back to oranges and grapefruits. I don't want to abandon that context yet. Suppose the distributions of grapefruits and oranges weights, which I'll call G and O, are independent and approximately normal. This allows us to do stuff. This allows us to do stuff. It has a mean of 17, or I should say, here's their given means and standard deviations. Note the subscript to see which applies to which distribution. If I ask you to find and interpret the mean, standard deviation, and shape of G plus O, then you should be able to do this. You should even understand what G plus O is. Out of my normal distribution of grapefruits, I'm picking a random one. Out of my normal distribution of oranges, I'm picking another one. And then I'm taking their weights and I'm adding them up. So, the mean would be just the sum of the means of the pieces. Mu sub G and mu sub O. Easy peasy. The standard deviations, remember, because we are independent here, we can do the Pythagorean theorem essentially. That allows us to conclude this. The new standard deviation is 0.79. And I think it's also worth noting that this new standard deviation is bigger than each of the individual standard deviations, 0.65 and 0.45, which should make sense because now we have a lot more variability, because I'm not just picking a random thing from a distribution once, I'm doing it twice with two different distributions. So it's going to be bigger. Also, remember, this is kind of like it correlates to the hypotenuse of a right triangle, and the hypotenuse is always the biggest side, blah, blah, blah. I also teach geometry. You get it. And then finally, the combined distribution is going to be normal because each of the other two parts are. Easy peasy. So with this bottom problem, if I want to try to deduce things about the distribution of SAT scores when I combine the math sections and the critical reading sections, which I'll call M and R, let's suppose I want to combine them not by taking their sum, but suppose I want to take their difference. What this would end up telling me is how much better people did in math than in reading. And if M minus R comes up negative, well, I guess that just means that people did better in reading than math, or at least for the particular problem that I'm looking at. So let's say this. Both distributions are approximately normal. I really should have said approximately here. And I have a big enough sample size that we can imagine it's still discrete, but it looks pretty continuous. If I want to find and interpret these things, again, center spread, standard deviation, or center spread shape, sorry. Let's see how far we can get. Oh, whoops, sorry. The interpretation. I kind of talked about these things already anyway. Back to grapefruits and oranges, sorry. I told you this would be sloppy. The average combined weight of a randomly selected orange and grapefruit is 23.5 ounces and typically varies by about 0.79 ounces. All right, back to SATs. So the mean of the difference would be 18. Again, in terms of interpretation, I think that's probably coming at the end, but whatever. This means that, on average, typically, students did 18 points better on the math section than the reading section. I guess another interpretation, if I choose a random math score and a random reading score, the math score will typically be better by 18 points. As far as the standard deviation goes, did you think this through? Did you think about how math scores and critical reading scores are probably not independent at all? Usually if a kid does well on one, they're probably going to do well on the other. That's not to say that people don't have their individual strengths, but I would not say that these two things are independent variables. And I hope we see why that means that we can't do the whole Pythagorean theorem of stats too. Because let me give another example of two random variables that are clearly not independent. Let's say like the number of hours that you're awake per day. For you people, it's probably like 18 hours plus or minus 1. So let's say like, I know I'm kind of going off track here, but like mu awake. Let's say your average awake time is 18 hours. Let's say The standard deviation there, I'm just like guessing here, is 1 hour. If I ask you, therefore, what's the average amount of time that you're asleep? Maybe I shouldn't have done awake and asleep because they both begin with A. Let's go S for sleep. That would then be 6, right? It'd be everything else from the 24. And then sigma sub S, let's also say that's like plus or minus 1 hour. If I ask you, what is the mean of A plus S? You tell me 24, because there's 24 hours in a day, right? If you're not awake, then you're asleep. And if I ask you for the standard deviation of A plus S, the Pythagorean theorem would yield us something kooky, but we know that there's literally no variation here, because if you add up the amount of time that you sleep per day plus the amount of time that you're awake per day, it's literally always 24 hours. And that's because being asleep and being awake are not independent things. So it's going to be the case that we have to very carefully scrutinize whether or not our two random variables are independent. And I don't think the College Board is going to throw anything too tricky at you. It should be obvious, if you consider this notion at all, whether or not the random variables are independent. So anyway, to proceed with this, the shape of m minus r is going to be normal. Why do you ask? Because both m and r individually are normal, so is their combined value. The interpretation, on average, I said that already. Okay, we're good. So here's a problem where, and I would really recommend trying this on your own when I'm done talking here, but I'm not just combining one random variable. What I'm essentially doing is combining 12. I'm choosing 12 random donuts. And remember, this is different from 6.2a stuff because I'm not choosing a donut for its weight and then multiplying it by 12. That would mean that all 12 of the donuts had exactly the same weight. We know that that's not how that works. But suppose that Dunkin' Donuts have weights that are approximately normally distributed, the mean of 9 ounces, standard deviation of 1.5 ounce. I imagine some toppings and icings are heavier than others. If boxes of donuts are filled by randomly selecting a dozen donuts, what is the probability that the sum of the 12 donuts is less than 100 ounces? So right away, we should acknowledge what we're trying to find is this. Probability that, let's say, t for total again, is our total random variable, that t is going to be less than 100. Sometimes due to random variation, it'll just be heavy. What if I choose 12 heavy donuts? Sometimes it'll be very light. We want to find the approximate proportion of times that it'll be less than 100 when I take the sum of the boxes. So if you want to take a second to pause this, I'll give a hint in about 5 seconds. So if you don't want to hear the hint, pause now and try it. Okay, here's some hints. Like I said, you want to make a new random variable called t, and we'll define it as this. There's 12 donuts, which is still the random variable d, with this mean and this standard deviation. And I'm using subscripts for each of these things. So I'm doing the Pythagorean theorem thing, but 12 times instead of with 2 things. Another thing is to consider the shape, the mean, and the standard deviation of t. And then how do we do that info? What does a problem that usually starts like this end up looking like? If we think about the mean, the standard deviation, and the shape, then it becomes very obvious. So the mean of t, the average weight that we would expect to find, if I reach into a normal distribution of donut weights and I grab 12 of them, what I end up getting is essentially 9 times 12, which is 108. The variance, and we don't have to do this with the variance each time. We can skip right to this formula. It's essentially 1.5 squared 12 times, so we could condense it to that, I guess, and then take the square root of that, and we end up with a standard deviation of 5.2 ounces. So we have the mean, we have the standard deviation. Here's the thing that makes this come together. We know that t is normal, and we know that it's normal because it's a sum of normal random variables. So if I take a random element of t, baby t, I should say random variable is t, and any element of it is little baby t. What's the probability that little baby t has less than 100 as a value? Well, since we know we're dealing with a normal distribution, I could essentially let this be my variable big T. We know that big T is centered at 108. We know it's got a spread of a standard deviation of like 5. So I guess one standard deviation on each side would put me at like 113-ish, and then, like 103-ish, a little bit less than that. And we're trying to find the probability that's going to be less than 100. So something down here on the left tail. You don't always have to draw it, but it's a good visual, and it might get you some extra points if you neglect something else important on the AP test. But yeah, we should be very comfortable with this by now. Normal CDF, negative infinity, comma 100. That's our boundaries, comma mean, comma standard deviation, and that gets us about 6%. So the interpretation, which didn't ask for, but it's never a bad idea to include it anyway, there's about a 6.2% chance that the dozen donuts will weigh less than 100 ounces. Fortunately, we didn't have to take into account the box or whatever, but if we did, we just add its weight on at the end, and then that's fine. If you hung with the middle steps, then you're probably just fine. But let's do one more for practice. Again, if you want to pause and try it, that'd be great. But otherwise, I'm gonna go. And also, we're clearly not doing this year. Kermit the Frog. He likes between 8.5 and 9 grams of sugar in his iced tea. If there's any other amount of sugar, he's gonna lose his mind. Suppose the amount of sugar in a randomly selected packet follows a normal distribution with this mean and this standard deviation. If Kermit selects and uses 4 packets at random, what's the probability that he's actually satisfied with his tea? So basically, we want to make sure that, or we want to know the probability that the sum of the 4 packets, grams of sugar, is between 8.5 and 9. How do we do this? We combine them. We let x be, or it doesn't matter. We'll call things. I'm calling it x, though. We're going to say that x is the amount of sugar in a randomly selected packet. It wasn't named in the problem, so I might as well name it here. And I'm dealing with 4 sugar packets, which all deal with the same normal distribution, so I'll take their sum. I'll call that t. We want to find the probability that 8.5 is, less than or equal to doesn't really matter with less than in a continuous random variable, which normals are. But basically, t is between 8.5 and 9. Whether or not it's inclusive doesn't matter. So, okay, mean, standard deviation. Again, note the whole Pythagorean theorem thing, but with a couple extra ingredients at the end instead of just 2 terms. And then the shape. We do need to specifically note that this is a normal distribution somewhere. The calculator command normal CDF does allude to that. But here's our boundary. We explicitly state it with a probability term, and then we see it appear here. Lower comma, upper comma, mean comma, standard deviation, and it gets us this. So there is an approximately 85% chance that Kermit is going to be satisfied with his tea. Great. It's a good thing this is a video. These problems are pretty rough. So it's important to not just understand why we're doing what we do, but for you to be able to do it yourself on your own. And then also make sure that you say everything that you need to say in order to scoop up AP credit. It's the same thing it's always been with the old normal distribution problems. State the mean, the standard deviation, acknowledge its normal distribution, list the area under the curve that we are acknowledging, the between 8.5 and 9 thing. So this concludes the video. Again, the year is 2020. I don't know how this is going to apply in the future, but you people at home, you do have a homework assignment, and yes, it's going to be a kind of big one because, like I said, section's a big deal. You don't want to put it off until the last minute, trust me. I threw some resources out here. There's learning videos associated with our textbook on this website, which I have linked in Canvas somewhere. AP Classrooms is doing cool videos now too. I think it's 4.9 or 4.8. I don't know. If anyone's curious, let me know. You can probably find it just by looking easily. And then also I have a link in Canvas to an explanation of the whole sum of variances Pythagorean theorem thing. It's actually more information than you need to know, but if anyone's dying to find it, it's there, and you can always go look at your leisure. Okay, that's it. Thanks for watching.